Okay, good afternoon, everybody. We're going to go ahead and get started. I'd like to thank you all for coming. My name is Vicki. I'm from the ODOT Research Office. We are here for the results presentation of snow removal wastewater disposal alternatives conducted by Dr. Christopher Miller and Dr. Bill Schneider at the University of Akron. Dr. Miller is here to give you a presentation on this project. For those of you who are participating in the webinar, if you have not done so already, please mute your telephone. You can do so by pressing *6. We're going to hold questions until the end of the presentation. Those of you on the webinar, on the lower lower left-hand side of your screen is a chat pod. You can feel free to type your questions there as they go along so you don't forget them. This report for this project will be available on the ODOT Research website. We will put the link into the chat box so you can get it from there. It will probably be up in maybe the next month or so. But with that, Dr. Miller.
Welcome. I'm Chris Miller. My colleague and co-PI on the project is Dr. Bill Schneider. This research project on snow removal wastewater disposal alternatives has been about a 2-year project. Before we get started on the results, I have to acknowledge this has really been a comprehensive effort with lots of input from multiple people. The research technical committee with Jamie Hendershot, who actually originated the research problem, the concept that perhaps ODOT should begin taking a look at. Hans Gucker and Tim Killeen. Tim was with ODOT and is now with the Ohio EPA. The entire research staff, we've had several phase modifications to this project, budgetary things. All of those required some work and effort, and they've been extremely supportive. As I detail the work that was actually done, we're very proud of and ODOT should be proud of the collaborative effort of 24, 25 different garage managers getting samples, multiple sampling events, and so it's been a complete statewide effort to make this project happen. Paul Enzinger from District 4 had some outposts that, as with the project progressed, that had some specific issues, and so he was brought into the project early on and has provided some cost numbers and some definite guidance. Mark Griffiths from Stark County deserves special mention. Again, we'll talk about some pilot unit results that we did, and he coordinated 4 different batch sampling efforts, and again, utilizing ODOT equipment and making that happen. There's also been an extensive team of graduate students, several PhD students and master's students that have worked on this. Looking at the research need, again, depending on the month, if you will, ODOT maintains approximately 240 maintenance facilities in Ohio. About approximately 80 of these lack access to sanitary sewer. Of those, mostly are outposts, 65, 66. The graphic down in the right-hand corner shows where those facilities are located. This was as of several months ago, and the reason I point to that is that you can see that it's a statewide issue. It's not necessarily concentrated in a specific geographic part of the state. Obviously, salt trucks are washed frequently during the winter to prevent corrosion. This generates a wastewater, if we want to call it, snow removal wastewater, also just refer to it as wash water. That wash water, after you wash the truck, contains suspended solids, dissolved solids. Dissolved solids could, primarily be the chloride from the salt. Obviously, it may also pick up some heavy metals. At least prior to this project, there's very limited data on the heavy metals that are present in that water, and again, the oil and grease, the normal things you would expect from roadway exposure. Only going to spend a little bit of time on the previous research. As of when we embarked on this, the primary research on this was out of Virginia and Indiana. Virginia Transportation Research looked at discharging the wash water directly from surface water with a permit. Again, because it has a high salt content, they concluded that that would require desalinization, perhaps with reverse osmosis. They looked at testing of that. It was ineffective, and getting rid of the salt was not the problem. The cost piece of that was the ineffective part. ODOT, at some of their facilities, via Purdue University, did a study in 2004. They looked at some treatment after oil water separators settling, and they reused the brine. Their water quality piece of that was primarily focused on suspended solids. There was not any heavy metals testing conducted on that report, which is a large gap. So we look at specific to ODOT and based on that research need, based on what had been done previously. As we looked, in some cases, the current disposal costs could be high. So particularly for commercial, collect it, then actually have to get rid of it, this cost could be as high as 50 cents per gallon. Then there was really three big, large unknowns. The volume of wash water that's actually generated at these, the nearly, again, 240 facilities, or the 80 that don't have access to sanitary sewer. What's the quality of that wash water? Again, we have an idea of what the constituents are in that water, but we have no idea at what levels and are they of any concern. And the real actual cost of managing that water had not been assessed. So we knew on an individual basis, maybe we're paying 50 cents a gallon, but if we start trying to look at this from a comprehensive standpoint and look at all of the factors, what really are the costs associated with that? So given all that, we need to try and see if there's a more cost-effective way perhaps, or what are those potential wash water management strategies that could be employed. So with that, again, there was quite a bit of information about roadway contamination. If you look at the side of the road, sediments, etc., but there was nothing, and I do mean nothing, about heavy metal concentrations or the wash water quality. So our first project objective was to actually begin looking at what other states were doing and for handling that wash water, and make sure that we didn't miss anything. Next, we wanted to make sure that we looked at what the current practices were across the state of Ohio. And then finally, we wanted to look at what were commercially viable solutions for managing that wastewater. So we weren't going to do a fundamental research project. We actually want to make sure that it was something that could be purchased off the shelf, manufactured, again, because if we have this large number of facilities, we want to make sure that it's something that can be implemented in a timely fashion. So for the project tasks, it ended up being two different phases. As I mentioned early on, we sort of set out on this project with the first 7 tasks that were phase 1, and I'll talk about those first. Those were, again, to look at the practices outside of Ohio, inside of Ohio, and the management alternatives, do some cost analysis of different strategies. We, again, different times met with the ODOT technical team, and then we wanted to develop and sort of look at a cost analysis tool for the different viable strategies. So we did that. We also did some preliminary sampling of the wash water quality, put together an interim report / what we thought may be a final report. At the time of the review of that report, it was decided that, and again we'll see based on the results of this phase 1, it was decided that we needed to get more wash water quality data and do a few other tasks. So phase 2 was implemented with 4 real distinct tasks from the first phase. First one is that we needed to update the cost analysis tool. So what that really meant is that for the different strategies, the different factors, whether it's labor, whether it's disposal costs, we were going to upgrade that to make it more user-friendly, more applicable to doing the analysis that it would need to do. Next was that we were going to look at 22 additional locations throughout the state. So we had 3 locations, but there was real concern whether or not those 3 locations would give representative results of the rest of the state. We wanted to develop some wash water quality models, and what that really was focused on is what are the factors that are contributing to the copper, the zinc, whatever that we're seeing in that wash water, and trying to identify those controlling factors. And then lastly, we wanted to actually do some pilot testing. So in phase 1, I don't really highlight it, but there was some batch sort of laboratory testing. We wanted to take it to that next level and get, again, some actual full-scale filtration media, cost-effectiveness type data, and then make a final recommendation. So please forgive me for the translation of this graphic. I tried to give an idea of the research sequence here. I'll back up. It's in the same order that we did the project task. But I at least wanted to highlight that the flow of this is that once we identified what the best practices were, on the left-hand side of the screen, remember I said these unknowns about the wash water volume generation, the quality of that water, this bench scale testing and pilot scale testing, those are really at the core of the analysis and things that we did and focused on that was a core part of that effort. And all of that information, again, which was an unknown, how much water we generating at a facility, depending on the length of time washing the truck, etc., what kind of quality do we have, all of that is going to impact whether or not a different management strategy is viable. And so all of that fed into what are potentially viable strategies, and then we do the cost analysis, etc. after that. Summarizing what we found outside of Ohio, we did a survey. We received response from 17 different state DOTs. We found out that 4 of those had tried reusing the wash water. Unfortunately, they used it primarily for truck washing, and so the water would get diluted, or excuse me, the salt content would get diluted to a certain point, but if you put that wash water and use it to wash a truck, you're putting the salt right back on the truck. So surprisingly, states didn't expect to see that, but it was a big problem, and so they discontinued the reuse in almost all those instances. Some would use holding tanks for it and then do commercial disposal or some other disposal means. 7, if you washed your trucks with water containing salt, that wasn't going to be beneficial. The water quality issue was primarily that it wasn't anything that they had measured or identified. They just had been told that they couldn't dispose of it. So again, there was a lack of the data that still was not coming back to us. None of the states interviewed reported monitoring for heavy metals, okay? So, or extremely limited outside of Ohio. The graphic I have, and again on the right, is just, I'll expand on later, but is a visual of, we found about 18 different versions of management strategies, and for sake of time today, I'm not going to go through all of those, and we'll focus on the 6 that we eventually narrowed down to. Outside of Ohio, again, there's about 80. Again, this number can change, be updated, but around 80 facilities that don't have sanitary sewer at different strategies of reuse. Henry and Meigs County. Henry County, we have a pond. They've been able to use that water. They do quarterly monitoring of the water quality. Some challenges associated with that have been that Mother Nature fills up the pond and you have to dispose and pay for water from Mother Nature. Relative to Meigs County, they've been effectively using the recycle treatment system, a clay-based system to try and take some of the heavy metals out. The cost for doing these things, again, commercial disposal, if you collect it and then dispose of it, can be as high as about 54 cents a gallon. The lower end, about 5 cents a gallon, is if you're able to dispose of it at a wastewater treatment facility. And again, different factors will go into that cost. When we looked at viable management strategies, there was about 18 different ones that were identified. We break it down at first level, if you will, as sort of a no treatment view versus a treatment view. And the no treatment view then further gets broken down to, are we going to do on-site disposal or off-site disposal? If we do on-site disposal, the first option that was one of the 6 that was identified as viable is what's typically done, is to go ahead and tie into the sanitary sewer. And this becomes our benchmark baseline case against which we compare the other 5 management strategies. So this was really where, in the early days of the discussion of the research project, was trying to look and see, does the assumption that tying in the sanitary sewer, is that the safest, most cost effective, etc. So it became the baseline option that we looked at. As far as off-site disposal without any treatment of the wash water, so in all of these cases you're collecting it, but you could collect it, store it, have a commercial operator come in and take the water away. That was option 2. Now when I say that these are viable, it doesn't necessarily mean that they're cost effective. These meant that these could be implemented at many facilities, could be done tomorrow, kind of thing. The third option is to actually take the water and haul it to a wastewater treatment plant using the equipment and personnel that ODOT has. The fourth option was to do disposal at a nearby ODOT maintenance facility using ODOT equipment and personnel. So, and the detail there is that obviously that facility would have access to sanitary sewer. That may have some other issues with it, getting approval of whatever the receiving facility is of that water. And I don't mean the ODOT facility, I mean the wastewater treatment plant or whatever is tied into that sanitary sewer. On the treatment side, we had 2 other options in terms of off-site disposal. If we treat the water with some kind of media filtration unit to remove heavy metal concentrations, we could get those to a safe level, if you will, an acceptable level for a wastewater treatment plant, and then take them to another ODOT facility and put it into the sanitary sewer. And then the last option was complete as treatment and then followed by reuse, which was media filtration to remove those heavy metal concentrations to a level that would be acceptable for reuse or brine. Now there's some hybrid overlap, if you will, some of these kind of things depending on how you want to look at it. We functionally wanted to look at no treatment and treatment as a path, as well as disposal versus reuse. And so some of these can get a little mixed, but I want to keep those words, if you will, keep those kind of clean and separate in your minds of no treatment, and again, disposal versus reuse, and what characteristics are associated with the different scenarios that we'll look at. So we said that one of the big unknowns was how much wash water are we generating, what's the demand, the potential demand for the use of that water. So just looking at the non-sewer access facilities, this graphic has them organized by district, and the blue line is the estimated annual volume of wash water that would be generated by those locations. The red line is the red bar is the annual 5-year average of brine use by those associated non-sewer facilities. So what we're trying to see is what's the potential supply of wash water, which it was based on survey records for the time of the wash, the wash rate, the water validated with some water use records, and that was about 3.8 million gallons. The amount of brine used by those locations averaged out to about around 6.5 million gallons. So from at least a volume standpoint, the demand for that water, the potential use of that water does exceed the supply. So it kind of makes sense, at least for those non-sewers, that you would have a means to potentially reuse all of that water. Looking at our sampling effort, again, this was broken down over 2 winter seasons. The first, we only looked at 3 sample locations. In winter 2012-2013, we had 24 garages. We purposely chose 1 garage in each district. And then we had 3 districts that we had a concentrated effort of roughly 5 or so facilities. Again, if you're looking at 240 facilities total, or 80 that don't have access, getting it, there was some balancing act here of cost versus the amount of data that would be collected. I purposely put up here that this was over 10,000 individual sample measurements. So I'll talk about the detailed things that were measured, whether it's conductivity or total suspended solids, but this was a monster analytical and collaborative effort to get these samples. During the winter 2012-2013, at those 24 garages, the goal was to try and capture at least 4 wash events. And by wash events, we mean after the trucks have been out, after the things have cleared, and bring them, whether it's 10 trucks or 12 trucks, and bring those in and wash them. That was a wash event, and I'll talk about some more of those details here in a second. So 24 locations, roughly 4 different wash events. Now, whether they occurred in December, January, February, whenever, we didn't specify separating them because we didn't want to impede any winter operations. And we can't control Mother Nature, but that was the limitation we had of 4 winter washing events. The sampling protocol for one of those events, and the details aren't completely necessary here, other than during a wash event, we would sample at the beginning, middle, and end of that wash event. So if they're washing 10 trucks and you wash each of them around 30, 40 minutes, I mean, that could be a full day of work of just washing trucks. The beginning, middle, and end of that would then just be at the start of that while they wash them, somewhere in the middle, again, because you had a different number of trucks at these facilities. We did not have a hard and fast standard method, if you will, here, other than the guidance of let's get the water as it first comes out of the oil water separator, let's get it during the middle of the event, and let's get it towards the end of the event. From each of those samples, we tested for 17 different heavy metals and 10 non-metal parameters. Again, in the final report, we have enough tables, etc., to look at. Of those 17 heavy metals, we pick up traffic metals. We also would have any of the sort of the non-expected traffic metals. As far as the non-metal parameters, we primarily had oil and grease, dissolved solids, suspended solids, conductivity. They are of primary interest of potential disposal or reuse regulations. Before I actually get into some of the specific numbers and the specific parameters, I wanted to give you an idea just visually when we started looking at those water quality results and we wanted to compare them against reuse and disposal guidelines, how would things sort of pan out? Now, again, I don't want to show you a table with all the different disposal and reuse guidelines here. The key thing is that because these aren't hard and fast regulations. Depending on the wastewater treatment plant, receiving facility, they may specify a certain concentration of copper. A different location may specify a different concentration. But we used actual values for these we used Ashtabula. We looked at some others for disposal guidelines that we compared the heavy metal concentrations and the total suspended solids and oil grease against. And then we used different aquatic environmental levels for reuse guidelines. When you look at this, again, starting at the sort of the 10,000 foot view, the parameters of concern, and by concern meaning they potentially exceeded these disposal or reuse guidelines, the following jumped out: copper, zinc, and iron. Believe it or not, there is actually an iron guideline and lead on the metal side, and then on with this non-metal side, oil and grease, and then total suspended solids. Looking at the graphic, there was only one in green garage where, regardless of the samples, all the samples were below those guidelines. But in general, we had a decent number of hits that were above disposal or reuse. And I'll start breaking that down for you on the next slide of how that looks for these specific constituents. If we looked at, again, there'd be 4 events potentially at a garage, 3 samples during an event. So you could have 12 different samples at a garage. So if we looked at the median concentration of those 12 samples, and we looked at disposal guidance of our 24 garages, how many of them, their medians, and on these different constituents were exceeding the local disposal guidance or reuse. So this first 2 columns has the garage medians. If you look at disposal first, very few of the metal samples, 4% of the copper, 13%, this of the garages on zinc actually exceeded. We had much higher hit on total suspended solids. 67% exceeded the disposal guidance. Converting that over to, or also then looking at the percentage of the garages exceeding the reuse limit. The reuse limits, the aquatic life standards, are much more stringent than the disposal standards. So you're going to have a higher percentage. And on copper and zinc, that number was above 70%. And the oil and grease, we actually had a hit of around 80%. So that's just looking at the median concentration. If you look at all the samples on an individual basis, so we don't worry about the garage, right? We just look at all 253 samples that have 17 heavy metals, 10 non-metals, and we look at the percentage of the samples. You see that the numbers are comparable to what you saw when you just looked at the median. Again, on disposal, TSS was the sort of the problem or parameter of concern. From a reuse standpoint, copper and zinc, again at around 60%, 66% of the samples were above the reuse standard, and oil and grease around 74%. So this allowed us to narrow down where the focus of potentially the constituents that could be of concern. Again, since we sampled during the beginning, middle, and end of a wash, this graphic shows, this is for Allen County Garage. It's looking at copper. There's 4 different wash events. The 1, 2, and 3 represent the beginning, middle, and end of that wash event. And what we found is that there's sort of a flushing effect where the first sample was the highest, and then during the course of a wash event, the concentrations tended to decrease a little bit. Without going into the details there, why that may or may not be, okay, the key was actually to see at least some sense of how much does it really vary during the beginning, middle, and end of a wash event. In some cases, it's quite a bit. Again, if you're washing 10, 12 different trucks, they're from totally different routes that they've plowed, different stages of cleanliness. A decent amount of variability was to be expected. We just wanted to get some sense of what that would be. So these are all, again, as a point of reference, the reuse standard for copper is just under 40 ppb. We didn't purposely pick on Allen County, but you notice the concentrations here are all well above 40 ppb. So summarizing some of these results, and we'll revisit them when we look at some pilot results and the ability to reduce these concentrations. We did compare them to these reuse and disposal. There really was a small number of samples that exceeded disposal guidelines. There was some TSS that's on the disposal side, but I think that's a simple fix or points to my last bullet here, which is the performance of the oil water separators. If you have high suspended solids, that just may mean that we're not quite getting the settling and removal that we would normally expect or should expect. And so in a collect and store situation, that wouldn't be a problem because the suspended solids are going to settle. So from a disposal standpoint, very few samples are really of concern. Looking at some specifics about the metals that we did see, we started to notice a difference between the particulate and dissolved ratio, and most of these, a significant fraction of these metals were in a particulate form. Again, the literature on what you find on the side of a roadway supported this, and knowing that it's coming from brake dust or from corrosion of the different vehicles, from exhaust, etc. And I'll talk about that a little bit more in a second when we looked at actually removing the metals from the water. On the modeling side, we wanted to try and identify factors that we thought were telling us that we're controlling or contributing to the levels that we were seeing. This first modeling effort was we took and looked at binary logistic regression models, and binary meaning just a yes or no, is the sample above or below a reuse standard. And so when we did that, I'll kind of cut to the chase later. The purpose of this was to begin trying to see if we could monitor for something at the garages that would tell us whether or not there's a higher likelihood that that wash water is going to exceed a potential reuse limit. So if we could monitor turbidity, which is a cheap analytical equipment, or a probe for conductivity, something you could just take a quick sample. Those was the idea behind this modeling, and we found that TDS, total dissolved solids, and turbidity were good surrogates and indicative of the oil water separator performance and or truck cleanliness. And when I say truck cleanliness, I'm not implying that the ODOT trucks aren't clean. It's just that depending on the degree with which they've been washed or exposed to roadway particulate matter, these surrogates then, if those were higher in general, they contributed to, they would let you know that there's a much higher likelihood that the copper or iron level would also be high in that wash water. Actually, I'm going to back up. We're limited today to talk about what's in the research report. We do have several publications where we've begun converting this to much more of a rule-based, if the turbidity is above a certain level, etc., that we're preparing and should be put out for publication soon. Okay, so looking at, we now know what's in the water. How are we going to try and actually potentially see about reducing those levels? We started out with some classic bench testing, and again, this was done in phase 1 to try and screen for some commercially available or materials that are available in quantity that could be used to remove those heavy metals. We looked at 4, 5 different media for this batch testing. The MAR systems, based out of Cleveland, Ohio, Sorbster media, which has been commercially available and used for mercury removal, arsenic removal from groundwater, performs significantly better than the other media. The media on the far right is actually just filtration sand. So if you're trying to get an idea of, without going into the effective diameter or what those materials, the one on the far right is filter sand that's commonly used in a drinking water treatment plant. So you get an idea that that MAR media is a fairly porous, durable material, large material, and that material, since it performed better, at the end of the phase 1, we reviewed and decided to move forward with the pilot testing. The first objective was to actually get a pilot type unit, get into column type testing, process large batches, something that would be typical that would have to be done at a garage facility. And so we purchased a pilot unit. We conducted all the testing actually at the university. The pilot unit is on the bottom left there. The red numbers, the 1 through 6, for different sampling ports. There's a 5-micron filter prior to the water being pumped through the filtration unit. So to get an idea of some size issues relative to the particulates before going into the media, what we did is we did 4 different batches where we pumped the water from the effluent of the oil water separator at the Stark County garage, pumped it into the anti-icing liquid, tank there, transported it to the university, and pumped it through the filtration unit. The capacity, the highest capacity for this unit is around 10 gallons per minute. So if you had, you could roughly treat, in an 8-hour, what's that, 8 hours times 60, 480, about 500 gallons or so in an 8-hour shift. I think if I did my math correct, right? Oh, excuse me, 600, yeah, my bad. 4,800 in an 8-hour shift, right? So 10 gallons a minute would be 600 gallons an hour, excuse me. So there were as much as about 1,000 gallons, 800 gallons in the largest batch, so it was really about an hour and a half or so to pump that through and treat that in the unit. The upper right-hand corner is just a picture of the media itself that come in those tanks and was hand put into this pilot unit. We wanted to make sure that the pilot unit itself could have any media put into it. So it's not necessarily MAR Systems. They actually outsource the hardware here and are just in the business of selling media. So we purchased the filtration unit. The filtration unit plus media was approximately $40,000. Looking at metal removal from these multiple sample ports, and again focusing on primarily zinc. The Stark 1, Stark 2, and Stark 3 refer to 3 different batches that we put through the unit. So those batches have varying wash water quality. We know what those details are, but we wanted to look at the removal as you went through that pilot unit. So the first bar on Stark 1, it's about just under 70% removal. That is after the 5-micron filter. So we noticed that we were seeing significant removal before it even went into the pilot unit. So that raised an awareness, if you will, that just removing 5-micron particulates from that wash water could have a significant effect on copper. Note that, again, when you look at Stark 1 versus Stark 2 and Stark 3, because you have variable wash water quality, there was less removal in Stark 2 for that 5 micron, and again was much higher on start 3. Zinc, which is the graph on the right, has a much higher dissolved portion than copper, and so you don't see quite that same removal due to the 5 micron filter. As you progress through the media, we could see additional removal, again, depending on this difference between dissolved and particulate, but these average removals for these different tests were at a fairly sufficient number, whether it's 79, 63, then 90%, depending on the different tests. Again, the reason we focused on copper and zinc was because they had the highest number of samples that exceeded the reuse guidelines. So they're the ones that we want to focus on at perhaps getting down to a certain level. So again, one of those unanticipated things on the path of looking at the results was this importance of the 5 micron filter, removing a large percentage, again, more so for copper than zinc, but we did some testing where we took wash water samples and we filtered them through a 5 micron filter to see what kind of removal efficiencies you would get. And again, these were some fairly high numbers. These are averages, but for some different samples. So we said, well, if we have these 5 micron particles, and we do some basic calculations to see whether it's 40 degrees Fahrenheit or the temperature doesn't have a large effect, it has some, but not a large effect, what kind of settling time would it take to remove those? So if the wash water is taken from the oil water separator, it's put in a tank, and you left it there, how long before the 5 micron particles would settle out? So because you have different density, copper, zinc is the reason you have different numbers here. The units on what's in the table are hours. So and the 2 meter, 3 meter was looking at different heights. So if you had a 2 meter, approximately 6 foot high tank versus a 9 meter, this was just to get an idea of how long before they would settle to the bottom. I put on there that for 5 micron particles at 3 meters for copper and zinc, anywhere from 11.7 to 15 hours, and those would settle out. So if you go to even smaller, which at 3 micron, those times go up, and again, we're not talking, weeks here. It's about a day and a half, 2 days, and those particles would settle out. So the question becomes, is the media actually doing anything, right? If the particulate fraction can be removed with settling, so we looked at the additional removal beyond the 5 micron, and again, since it's going through a filtration media, we don't know completely whether the removal mechanism is filtration of the particles less than 5 micron plus just absorption of the dissolved phase of what's going through there. I present all 4 metals. Again, I think that copper and zinc are important to look at. Again, details of this are in the report. Zinc had a much higher dissolved phase in what passed through the 5 microns. So these are results, again, of what was less than 5, and the media was very effective at removing zinc. The reason it looks like it's less effective at removing copper is because a good amount of the copper has already been removed by the 5 micron. So the media, this affirmed that it was actually doing something at again, these are average values for the different tests, anywhere from 46 to 79% depending on the metal. So all right, looking at the cost analysis, and again, this was focusing on the 6 different viable management strategies, which are on the left-hand side of the table. We will talk about here in a minute the cost analysis tool that we actually developed is completely customizable, which was one of those upgrades from phase 1 to phase 2. So the values that are here were what we used when we did our initial preliminary cost analysis, but the cost analysis tool allows all of these to be varied. The key here is to look at the factors, the big factors that were involved. For the sanitary sewer option, it was simply what was going to be the tie-in cost, the capital cost, permitting, etc., single value. For commercial disposal, for hauling and disposal, that we put in there 30 cents a gallon. We had seen that the payments had been made for as high as 54 cents a gallon, so we lowered that down to around 30. And again, these are the baseline numbers when we wanted to look at some different scenarios, which I'm going to talk about in the next couple slides. For all of the hauling and disposal, we took ODOT labor rates, we took normal equipment rates, all those kind of things that are fuel, etc., into account. The basis for looking at these was looking at the equivalent uniform annual cost. So whether we assumed a life of 40 years for sanitary sewer or 70, again, all these things were eventually brought down to an annualized capital cost. The filtration unit lifetime as well, whether it was assumed that that was 10, 12 years, again, all those things could be modified in that cost analysis. Looking at some of the things here, again, you have to, each facility has a different number of trucks, has a different number of winter events that they're going to be washing those trucks. So you have to kind of go with the baseline to try and look and see where at least some of these numbers, again, where they break down, where they're going to fall for what's going to be more cost effective. For this graph, looking at the different strategies, this is what we call the high volume location. High volume location could be a facility with 12 trucks, 30 events, a round trip hauling distance of 55 miles. So if, when we looked at GIS information, we saw that take 50, I don't know why that's not an even number, right? That would be, I guess that'd be 27.5 miles one direction. That another garage or a wastewater treatment plant is certainly within 27.5 miles of all of those facilities that didn't have sanitary sewer access. So the furthest hauling distance, a high volume, and we found that if, again, these are all relative to the sanitary sewer tie-in cost, that if sanitary sewer was $173,000, 600 or 173,640 or less, it was the most cost effective for the high volume, assuming those baseline kind of conditions. Once you get to about 285, all these other alternative strategies start to become more cost effective than tying into sanitary sewer. And again, without getting into the details of disposal versus reuse, the assumption here was just strictly looking at the costs, not whether or not it would be in compliance. It's assumed on the reuse strategy that it would be allowed to be reused, etc. Looking at a low volume location, the numbers low for the sanitary if it's so 95,000 or less, it's the most cost effective. Once you get up to only about $200,000 to tie in, all 5 of the alternatives become more cost effective than the sanitary sewer. And again, we can debate the numbers, but at least now there's been some idea of where is that potential line in the sand where doing something else becomes more cost effective. So whether it's 173,000 or 95,000, somewhere in this $100,000 to $200,000 range, if tying into sanitary sewer is more than that, these other alternatives are going to be more cost effective, is where we started to see. So, and just as a point of reference, again, at least 4 or 3 of the outposts in District 4 that we had cost estimates for just around $330,000 or $340,000. So it tells you that looking at these alternatives is probably the path to take. Wish we had time to do a demo, if you will, the cost analysis tool. You have a visual of this. The piece on the left with all the red boxes is the different user inputs. So whether it's the number of events, winter events, wash events, the number of trucks at a location or facility, the different interest rate for the financials, the planning period for the sewer, whether it's 40 years, 50 years, all of these were allowed to be customized and input. We even have the analytical monitoring costs in there if a facility is going to take it to another location and dispose of it, and you have to sample quarterly, monthly. If you know what those costs are, all of that could be put in there. The middle portion of the tool shows the annualized cost. On the far left is the sewer tie-in, and then the other 5 alternative strategies. You get to see just real quickly the one that's much higher. There's that commercial disposal, which again we've seen time and time again. The actual values are in the last third of the spreadsheet for the annual costs and the potential annual savings. Again, this was for a single garage. So if you want to look at the specifics, which is really how it breaks down and modify the number of trucks, events, etc., this is how this was set up. We did have another version of the tool that looked at things from a district-wide perspective and some optimization and some things, but again, for the sake of time, not presenting that today. All right, before talking about the implementation and recommendations, any questions, just summarizing again that we looked at best practices, came up with these 6 what we considered viable strategies. I like to say that we have, or ODOT has, I say we, the largest wash water quality database on planet Earth. So, and I'm now on record again with why darn it saying that. So unless if you have more than 13,000 measurements, this again was a huge effort. And again, not a surprise at what those were, but we now have an idea of what those concentrations are for copper, zinc, etc. in that water. We did some modeling to identify some things that perhaps could be used as surrogates for monitoring that wash water quality. We did some pilot testing. We didn't anticipate, part of the wash water characterization was not a particle size distribution analysis. Again, we were working within certain limitations, etc. But once we just started doing the testing and found this 5-micron part, that allowed us to look at settling at least as a partial removal alternative, and we calculated that time anywhere from 12 to 15 hours. We found the different factors, incorporated those into this cost analysis tool again, which depending on the assumptions, anywhere again around 95 to 170,000 before these other alternatives become a much better choice. So looking at some recommendations for implementation, I've tried to organize this by the time frame, and so I think the things that immediately could be moved forward versus some that here in the future. Immediately, I think that for all the locations that do collect and store, if we allow at least 24 hours for settling, as well as we ran into issues with transport into from Stark County. As you can imagine, even though we have the finest roads right in the country, there's a little mixing that's going to take place, and so we had a nice particulate mess that exacerbated our particulate problem. But you'd want to make sure that when you actually pull off the storage tank that you take steps to minimize particulates being mixed, etc., into that wash water. no matter what, this is a good thing then. Those heavy metal particulates are going to settle to the bottom of the tank. Sure, you're going to have to manage those, but you're not going to be disposing of them at the wastewater treatment plant. The second item, for all the locations that pay for commercial disposal, if there are still any of those, investigate certainly disposal requirements at a wastewater treatment plant. Indeed, this is what happened with one of the outposts in District 4. We were able to take it and reduce that cost substantially. We think that this large database, again, provides the justification for what that wash water quality may be. Again, immediate cost savings is very likely. Eliminating commercial disposal is an option. The third bullet is to actually use this cost analysis tool to determine site-specific costs and assess, rank wash water management alternatives for all facilities without access to sanitary sewer. Again, we could have do that. We had an inventory of the trucks, et cetera, at these facilities, but there's going to be some manager input or even a high level at the district level, look at these things and assumptions that other than those basics, we weren't comfortable with making. It would kind of have to be looked at in some almost uncertainty analysis as well, assuming the number of winter events, those kinds of things. But you can at least now begin looking at these individual sites and calculating what those potential savings may be, and at least that can be quantified so that they could be ranked. Might as well at least now, we had no idea of those 66 outposts, which one of those has potentially the greatest cost savings, and could begin focusing on that location as a starting point. In terms of the next year, I think that we're going to take the filtration unit from the university to the Meigs County garage. I think that next year that it could be used to replace the current recycle treatment process that's used there. I know that the current process is a little bit labor intensive, so I think there would be an immediate cost savings there, as well as an improved water quality of brine made from that wash water. As far as the second bullet is that we should actually monitor the filtration unit performance and operations. So we have the 3 large batches from Stark. It'd be good to go ahead and get actual additional unit performance during multiple wash events, etc. And the operations piece there, I think, is important. Again, we didn't run into any operational problems, but we only ran the unit hardcore on like 4 batches. You know, what happens after 15, 20, cleaning the media, those kinds of things, you would want to actually begin looking at that. The third bullet, for locations with the potential high cost savings, could actually begin creating a plan or strategy for moving forward with those. So depending on what is going on with those locations, we've created kind of a schematic, or looking at that this is where you can monitor some of these other surrogates. Total dissolved solids via conductivity probe, turbidity, and iron were all excellent surrogates for seeing whether or not the wash water quality is good or bad from a reuse standpoint. So no matter what, you're going to have to collect it, store it. You let it settle. The graphic shows, and again, the calculations, you can remove 50 to 80% of that water. If you take a sample and do the conductivity, turbidity, what we're doing right now is modeling and seeing that with 80%, 90% accuracy, we can flag whether or not that sample is going to be high or not. And if it's not going to be high in terms of reuse, that may be justification for being able to reuse it. If we think that down the road it's going to actually require even a higher level, then you go into that treatment box, and we said that you can get an additional 20, 30, and this is assuming after the particulates are settled and gone. And then finally, the long-term recommendation is that, I mean, obviously one winter season could do this again for, continue to use that, monitor its long-term field viability, use these surrogates to see how they actually correspond with the high copper and zinc or lower copper and zinc. Again, want to make sure and validate that that indeed is the case. And then I think you could actually begin discussions on the widespread potential reuse with the Ohio EPA and the different applicable regulations. Right now we know that disposal is accepted, is fine, the guidelines, all these values from these look, but we know the challenge with trying to move forward with raising awareness on the safety or perceived safety of using it for reuse. And I think that coming up with these surrogate parameters, they're cheaper, easier to use, would be the path to suggesting, again, validated with at least information from Meigs County Garage that that's a viable strategy for moving forward. And that's it. So I'll take questions at this time. Yes?
Did you get any estimates on the volume of the wastewater created?
Excellent. So that when we did the non-sewer volume, there was like 3.5 million for all the facilities. The number is anywhere from about 300 to 350 gallons per truck per wash. So if you know, depending on whether you have a high pressure, low pressure, that's sort of the benchmark number. So if you have 10 trucks at 350 gallons, you have about 3,500 gallons of wash water for that one event.
Which one event would happen no more than, it wouldn't happen more than once a day?
Well, correct. At the end of the winter, right at the end, you know, depending on, again, we had that 30 washes, 30 winter event was on that higher volume end. That's where we know some years that number may be 20, others it may be 40. We're actually doing the calcs on an uncertainty analysis that rather than just assuming a fixed value that wasn't part of this report. But
so 350 gallons per truck, and if there's 10 trucks, 3,500, 4,000 gallons.
Right.
What that sentence seems to me is with the need for 24 hours minimum of settling time, that the rules that engineers are using to design oil interceptors, grease and oil interceptors in garages are bad. What the rule in the state of Ohio is 1 cubic foot of storage in an oil interceptor for every 100 square foot of garage space, and that generally yields interceptors that their effective capacities are 500 to 1,000 gallons, maybe on the high side. So what you would need to get 24 hours settling for 4,000 gallons obviously would be a 4,000 gallon minimum effective capacity for an oil interceptor, and that is very, very unusual to see anywhere. And my company builds oil interceptors and based on the Ohio Plumbing Code, and that's what the designers use is the Ohio Plumbing Code. I think the biggest thing is the oil interceptors are undersized for the amount of settling that you are identifying.
And so it's an excellent point. And we obviously the suspended solids data, that other data supported that they weren't built to get effective removal, right? Given the capacities, they're undersized, right? So now the question becomes, do you want the storage in it's an engineering question, do you want the storage in the oil water separator, or do you want it to go ahead and have it be external, so you pump off? When I say that collect and store stage in the graphic, we're thinking, which some of these do, is they actually have the above ground storage and they pump it from the oil water separator, and then you get the settling there.
Mm-hmm.
So it's going to be some right now that capacity is there as part of where it's 5,000 gallons or 8,000 gallons. Some of that's kind of being built. That's probably, initial gut is where we would have that happen. I mean, depending on, or you could push for, I don't know what's the most cost effective. That wasn't part of the scope of there, you know, where you should get that storage. You know, and it's a good question though. Any thoughts there, Gene?
Just that, you have to repeat my answer, sorry.
Right.
Just that, you analyzed oil and grease as one of the components, and you didn't see big problems there to meet a reuse standard. So yeah, as Chris said, we're running through the oil water separator. You make a very good point about is it sized appropriately, but the settling was occurring, with those heavy metals, which to my knowledge, an oil water separator, the purpose of that, the intent is not to remove the heavy metals, it's to remove the oils and greases.
So the discussion is whether or not we want, again, that trade-off in the volume. I think, though, that TSS in some of the oil and grease was even exceeding disposal guidelines, though. So suggesting that, again, the performance isn't meeting what you would hope because it's of the high throughput. So, I mean, that it's not that they're built incorrectly, right? They're just undersized. If they were the sole line of defense, and so who knows? So you could, if you started looking at that, I bet that's common. When you're washing 10, 12 trucks and pushing through that much volume, they're undersized. So,
They are.
yeah.
And your comment that their oil interceptors were put there to intercept oil and grease, but if you identify that with 24 hours of settling, you can get some of the heavy metals out of it, then it's doing something no one really had designed it for.
Yeah.
But there are simple ways to decant a vessel and not disturb the bottom
Right.
layer of that vessel, and
Right.
so the storage in place is probably pretty cost effective, I would think, if it's in place in the original oil interceptor, if it's big enough.
Yeah. Yeah. Okay, an online question. Vicki, do I just need to scroll to the,
Need to scroll.
or is it Sam Myers?
Yeah, keep
Okay.
right. There's a Laura Fay right above, two above.
Okay. Can other states use the tool developed? I know the report's available online.
Yes, the tool will
Yes.
be posted online when the final report is available.
And it's an Excel-based spreadsheet with the details in the report, so it will also be made available, I'm being told.
Mhm. Sam Myers.
And recommendations, revisions to that tool, anybody would use that, feel free to relay those to myself. We'd appreciate that. Another question is, after the water is initially settled and is pumped, what are the procedures for dealing with the remaining water with higher levels of contaminants? So this depends on its the disposal versus reuse category. So if it's for disposal, in most cases, it's just going to be able to be safely disposed. The levels will not be high enough after settling that you would run into any issues. So you could take it to another ODOT garage that has sanitary sewer, or you could take it to a wastewater treatment plant directly and dispose of it. If it was for reuse, then you're going to have to measure, which is in the graphic still on the screen, you're going to have some measure or means to tell you whether or not it's above or below reuse. And that's the point of the conductivity, turbidity. Those are our cheap screening tools to tell us, okay, here's that water, it's been in the tank for 24 hours. We take a sample. If the conductivity, turbidities are still at certain levels, we know with 80%, 90% confidence it's above reuse. Okay? And so then, at that point, you just safely dispose of it, or you're going to have to do some treatment, or that's still the wild card, relative to what the applicable reuse guidance is, which we said there is not, that's not hard and fast. So,
Curious, on the water sample, untreated water sampling, or water before it was used as wastewater, to kind of get a baseline for all that, was that taken actually out of like the power washer or anything like that, or
good.
itself, or just with the thing, all the copper and other metals injected inside the washing unit itself, or not?
Right. So the question is that was the wash or excuse me, was the water quality of the water used to wash the trucks tested? And the answer to that is no. We knew the source in many cases, whether it's a municipal like surface water system or whether it's well water at the location. We know what a typical dissolved solids value is of water from city, you know, and so the values that you would see as a baseline are very, very negligible compared to the values that you see, you know, from once salt gets in there, right? The dissolved solid spikes dramatically. So, you know, so we didn't measure that quality because we didn't. We know it's a minor factor, but it's not the controlling factor to that quality. At least that's. So far, there's no indication that that would be critical. I mean, we know well water can have sometimes a little bit higher iron or something, but it's going to be dissolved. It's not going to be particulate. So that's that whole, start getting into what's the real source of the contamination. The primary form is, you know, is particulate, and then it dissolves once it sits in oil water separator or wherever, starts to do some different phase changes. I see someone's typing a question. Any other questions internally to see
what type of filter was it that you used for a 5-micron filter? Was it some type of a fabric or?
Yeah, this is that I'm trying to think. I don't know exactly what was on the Mars Systems unit. I have to be removed. Yeah. And
I wonder if commercially getting 5-micron for what 4,000 gallons a day.
No, that's a pain. No, yeah, that's where we started running into some plugging issues with that first batch. You see why but we rectified it with some of this. I think that's where that settling piece, all right, you remove a lot dramatically in a short period of time, that it then becomes somewhat of a non-issue. But no, that's one of those operational things. And we even looked at some different bag filters, some other bulk kind of things that that we have information on that we're going to pass on when they actually start trying to do larger quantities. And any other questions? Maybe just touching the keyboard. It looks like the question. Oh, it is. Okay. Question, did you look at each facility independently and look at washing trucks at commercial wash facilities rather than having to deal with the wastewater on site? Again, I think because of the magnitude or scope of trying to come up with solutions that could be implemented for all of ODOT, we didn't look at commercial washing. Again, we have lots of rural outpost facilities. The cost of driving to, I'm sure there are some viable commercial washing facilities available, but we didn't look at that as I know that a couple states had mentioned, I think they ended up trying to build some centralized washing facilities as one of the possibilities of dealing with this, and then I think it was very cost effective, again, because of trying to get them centralized enough relative, as I showed initially in here, you have about 240 facilities spread across this large geographic divide. In some cases it may be viable, but as a standard across the board, we didn't look at it. I believe it was Minnesota that had again, when you have the large number of trucks, like around Minneapolis, and sometimes they built some of these larger scale washing facilities. Any other questions? vote.
Okay, if there's no questions, we're going to go ahead and conclude the webinar. We'd like to thank everyone for participating. If you have questions you come up with later on, you can feel free to email those to research@dot.state.oh.us, and we will forward those on to Dr. Miller for him to respond to you. I'd like to remind you once again, the final report will be available on the research website. The link is in the chat box. If you scroll up, you can see it. As well as this session has been recorded, and it will also be available on the website that you can go back and watch it later and get a PDF version of the PowerPoint slides that Dr. Miller went through, and share the link with your friends and colleagues who weren't able to join us. We'd like to thank you all for participating. You're free to go.